Morning. So last week I discussed a little bit the Hilbert, Deluxe problem and how it can be coded using some very basic model theoretic construction or geometric construction of what I call the forward progression map. And at the end, we singled out the pieces of that progression map as what we call a correspondence map between two cells in that cell decomposition that we fixed. Okay. And so now, in some sense, right, that's all that I can say in that kind of generality. So from now on, in order to say a bit more, I'm going to assume that my vector field is real analytic and goes into S2. Right, so we add a point P at infinity, the pole, and we throw that singleton into the cell decomposition that we had from last week. Okay. And so in this situation, I would like to study
from S2 to R2.
From S2 to R2, yes. Good point. It's on S2 into R2, the tangent space at every point. Okay, so so the first observation is purely o-minimal. I leave it as an exercise, right? If you have a map, in fact, that's still about o-minimal map. If you have a map on S2 into R2, then you can have at most codimension 2 size set of singularities. Okay, so in this situation, all but finitely many singularities are removable. Okay, because codimension 2, of course, being a definable set, means it's finite.
But if you have a function like that, which is not identically 0, then it can only have finitely many singularities.
Yeah. Well, you can. What do you mean? It's a vector function.
Oh, right. You can have a line of singularities.
You can have a line of zeros, right?
Oh, yeah. Okay, sorry.
But from the point of view of a vector field, they're removable, most of them.
Oh, okay.
Right, and for that,
yeah,
you need the idea that a definable function, a definable bounded function on a set can at most, extends almost everywhere, in the sense of, except on a set of codimension 2, continuously to the boundary of the set. That's what you need here. But yeah, I leave it as an exercise. Okay, so we are going to assume that the set of singularities is finite. Okay, so we just have finitely many singular points in our cell decomposition. They appear in our cell decomposition. And so now we are going to look at what we call a correspondence map in this situation. So let's just draw a picture again to fix the ideas, right? So in this situation, a typical, and I will explain a bit more what I mean by that, correspondence map looks like this. Okay. So remember, we had a situation where we may have a cell in our cell decomposition, an open cell, right, whose boundary is made up of cells in the cell decomposition. And since we have only finitely many singularities, let's just say only at most one of the endpoints, one of those bounds and boundary is actually a singularity. Okay, so this point here may be singular. This is the same picture that I've had up before. I'm not trying to be highly original here. So it could be that here we have a tangent piece and another tangent piece. Right, so the blue ones are tangent. And then the flow or the forward map will correspond to this kind of situation. Right, so if this cell up here is C1 and the cell on the side here is C2, both transverse, right, we have the map G, C, C prime, which maps things from C into C prime or from a subinterval of C to a subinterval of C prime. And then what I did last time at the end is we transported this definably back to studying the germ of a function. Sorry, I called this F, C, C prime, to studying what I call G, C, C prime from 0 epsilon to 0 delta. Right, so by coding a piece here and a piece here, introducing definable coordinates, and then pulling the back, FCC prime back.
You mean FC1, C2?
C1, C2, yes. Right. Okay, so it's these maps here that we are going to study in some cases. So far, so good. Any questions? That's just the kind of the review of what we did. By the way, this kind of picture that I'm drawing here, right? This has a name in the literature. It's often referred to as a hyperbolic sector. There's a lot of terminology that's related, and people use different exact terminologies for the same thing. Most of the stuff I've been doing preparing my lecture today is chasing the different terminologies and figuring out again which is which agree and which don't. But this kind of name is used a lot for that kind of picture. Okay. Okay. So the question right now in practice becomes, how do you study, right? How do you study this kind of germ? And the first step, which I'm not going to do, which you saw in Daniel's course last month, right? You reduce to certain types of singularities, but that gives you more information, and you do that using resolution of singularities. So using resolution of singularities, in this case, we are just looking at resolution of a single real analytic vector field on the plane or on the sphere. And I believe this is usually credited to Dumontier, even though Deluxe already did a lot of that in his paper. But right, and if you remember, resolution can only be used so far. You can't make the singularities disappear. But we may assume each singularity is elementary. And elementary has actually an easy definition in the case of characterization, in the case of real analytic, which you might also remember. If, right, these are C1 vector fields at least, right, they're real analytic. So and then we have the associated Jacobian matrix, right? Is the Jacobian matrix of all partials of C. Then Z in S2 is an elementary singularity. Exactly if at least one of the two eigenvalues of the Jacobian matrix at Z is not 0. One of the eigenvalues of G of C at Z is not 0. Right, so the Jordan decomposition has a diagonal entry that's not 0. So all the other singularities, we can make disappear just using blow-ups and so on. Of course, when you do that, right, you're not strictly speaking talking about a vector field on S2 anymore. You're replacing S2 by another compact two-dimensional analytic manifold, even algebraic in that case. But that doesn't locally change the picture. Right? It simplifies it though when you study these kind of correspondence maps. Okay, so that's and so then the big step here is Ilyashenko. Proved that all, no, I'm not going to say what he proved, it's too complicated, was able to study all correspondence maps near elementary singularities. Right? And remember, we were interested in the question whether these correspondence maps we're interested in the question whether this correspondence map can be can reconstitute the global what we are called forward progression map, and then show that the fixed point set is finite. That was the question, right? And he's able to do that and prove Deluxe problem. So he can give us, right, he can find out enough about these correspondence maps to at the end be able to prove Deluxe problem. Now, okay, I'm going to just, this is only for information and motivation, that my goal is not to do that. Okay, my goal is to understand these kinds of correspondence map near a hyperbolic sector. That's what I'm going to do forward. But I want to just describe that's not all he has to deal with. Okay, so as a bit of an aside, let me just tell you what is involved here in this thing. And again, I'm not going to prove any of that. I'm just going to give you a little bit of a summary. So what he does is that he starts from a fairly well established, right? There are 4 types. Actually, there are 6, but 4 pictures, right? There are 4 types of pictures of the phase portrait of such vector fields near an elementary singularity. Okay, so the 4 types are that you can have a center or a focus. So something like this, right? Where your singularity is. So a center would be where the leaves are all circles instead of being spirals. Okay. Then there is the situation where you have only hyperbolic sectors. So the typical picture would look something like this. Right, so in each quadrant, so to speak, we have the picture that we have here after deformation. So this is called, what is this, hyperbolic? No, this is called a saddle. Let's see, what else do we have? We can have what's called a node. And that's where essentially everything goes into the singularity or comes out of the singularity. Okay, that's another possibility, topologically speaking. And then the final one is the so-called saddle node, which I'm going to quick picture. So a saddle node is kind of the mixture between those two here, where on one side you have the picture of a node, but on the other side you have what looks like a hyperbolic sector. So you have 2 hyperbolic sectors and then a node picture on the other side. Okay. And for elementary singularities, these can actually all be characterized in terms of the eigenvalues of the Jacobian at these points. So let me also say what those characterizations are. So for the center focus situation, right? So this is a 2x2 matrix. It's a real 2x2 matrix. So the eigenvalues are the roots of a real polynomial, which means they are either both real or they are complex conjugates. That's the only option. So this is the this is the case where they are purely imaginary. Eigenvalues plus or minus I times omega for some omega. Okay. The saddle case, that corresponds to 2 real eigenvalues of opposite sign. So you can actually read these things off from your definable vector field, right? So 2 real eigenvalues of opposite sign. In the node situation, we have, what is that again? That's when you have complex conjugate eigenvalues with non-zero real, no?
Excuse me, Patrick. Sorry.
Oh, that's the complex conjugate. Yeah. Sorry. Yes.
Yeah. In the first case, for center focus, you can also have complex conjugate eigenvalues with non-zero real part.
Oh, same as for.
Yeah, in the center focus. I mean, yeah, the center focus is just that you have non-real eigenvalues.
At the saddle node?
No. For the center.
Yes. Oh, sorry. Yes.
Yeah.
Okay. So here, the complex conjugate case is the center focus case. Yes. Sorry about that. Right. And the node case is two real eigenvalues of the same sign, non-zero. Of the same sign. Okay, and then this is the case where one of the eigenvalues is zero, but the other is not. Okay. So, right, so each of these you can actually find out just by looking at these eigenvalues. Now, let's see. If we are in this situation, right, in our cell decomposition, we would have something like these quadrants here. Okay. In this case, it's a theorem, and as far as I know, the only source, the only literature source for proof is Andronov's book, the second book on ODE theory, which actually says that the correspondence map in this case is definable in our subband. Okay, even when we have so if we have straight lines here like that, it's real analytic, and if instead of straight lines we have, you know, definable cells like that, then it's definable in our subband. So, from the point of view of studying these correspondence maps, this case here is all right. Right? We do actually understand that. Now, for Deluxe problem, this case is not actually interesting because that doesn't interfere with finding fixed points of the progression map. But still, it's good to know. Let's see. In this case, well, if I have my cell decomposition close enough to include something like this neighborhood, right, then all the correspondence maps on cells outside here are trivial. If they go in, right, they're all the constant map infinity. If they come out, they are the empty maps because there is no correspondence map coming out of a singularity. So this picture here is okay because it doesn't, there's nothing to study. So the ones that we need to worry about is this and that picture over there. This is the one that I'm going to focus on for the rest of the lectures, because that's the one I kind of understand now. This is the one I don't understand. I'm beginning to understand, so if at all, right, this could be a topic for a mini workshop after courses are over. So this is what we're going to look at. This one we will not look at. Okay. But I will be very happy to look at this afterwards, like I said.
When you say you understand the saddle case, this means you understand it from a point of view of o-minimality, that these.
No.
Or
I'm just understanding the nature of these maps at the saddle hyperbolic sector, in other words. Right? So this saddle case is called the hyperbolic singularity. Okay, that's all. No, I do not know about the minimality of these maps there yet. Okay, so I will tell what I know, and in that case, even less. Okay, so that's the case I'm going to be focusing on for the rest of the whole course. Okay, so we assume from now on that all the singularities of C are of this nature. Right? That all singularities, right? And this is kind of an arbitrary choice. It's just because that's what I know something about. It's not because that's it does not cover the. It's not enough to figure out.
Excuse me once more. Sorry, Patrick. Excuse me once
Yes.
more. Maybe well, the picture of a saddle, you can also have this picture of a saddle when there is only one non-zero eigenvalue. It depends on the evenness, on the restriction of the vector field to a center manifold. Yeah, are you assuming that the two eigenvalues are different from zero and of different signs? Okay.
Yes.
Yeah.
Right. So two real eigenvalues of opposite sign.
Yeah. Yeah. It's
both non-zero and both of opposite sign.
Okay.
So everything else I'm putting under the saddle node case.
Yeah. Okay. But yeah, in that case, you can have also saddle or node entirely, but doesn't matter. Okay, thank you.
Okay, but yeah, the node case doesn't give us anything interesting to look at. Okay, so we assume from now on that all singularities of C are hyperbolic. Their product, a short way to say this is that their product is less than zero. Okay.
what do you mean product? What product have you doing?
Of the eigenvalues. Sorry.
The product of the
Product,
okay.
so product of the eigenvalues is less than zero.
And they are real.
Yes. Well, otherwise it wouldn't be less than zero because there would be complex conjugates. So their product would be positive.
Okay, I see.
Right?
Yeah.
So that is a very short way of coding hyperbolic. Okay. So now what I have to do next, I will have to introduce some new terminology, right? So I really would like to understand these maps better. And this will require us to delve into a bit of analysis. So let me start by stating the fact that I also will not prove, again, because this is about actually looking at, right, at the analysis of these maps. I just take this as a fact by Ilyashenko. So in this case, each correspondence map of C near a singularity. So I consider this a map from 0 epsilon to 0 delta. is what he calls almost regular. That is a pretty terrible terminology because it involves two words that are completely overused in math. But that's what they're called. And so I'm going to have to spend a bit of time to explain what this means. This is quite, it requires us to introduce terminology that I will use for the remaining time of this lecture. Okay. So what is this almost regular? All right, and I will need this tablet here to help me with this. So as a definition. Okay. So for example, if it's a real analytic at 0, it's almost regular. That's the easiest case. Okay, but it does not require that. It extends the notion of real analytic. So consider a map on some interval to the right of 0, a function, real function. Okay, so this f is called almost regular if, well, the following data exists. So as a starting point, maybe as a motivation, right? Let's remember, real analytic means that it's given by a convergent power series at 0. Okay. So almost regular is a bit of an extension of that. There's still going to be some sort of series that determines the function. Okay. But there has to be other conditions that make sure that it does determine the function, because the series in question is not going to be a power series. It's going to be a Transseries, a very simple one. And it's not going to be convergent either in general. So here is what we need. So I need some data to describe the series, the Transseries in question. So we have a sequence of exponents, all bigger than 0. And alpha 0 less than alpha 1, and so on, going off to infinity. Okay, so that's still powers, they will be used as exponents in a series of Transseries series of simple kind. There is a constant which has a space, plays a very special role. So I'm going to call it C0, and it's not 0. That's a coefficient, a very special one in the series. Then the other coefficients in the series, so we have a power series, right? These are the exponents, x to the power alpha I. It's not a standard power series, it's generalized power series.
They are real, the alpha.
They are real, yes, right? So these are real alphas, not natural. First coefficient is going to be just a constant, that's not 0, that's important. And the other coefficients, though, they are not constants, they're polynomials. So polynomials, pi of x, with real coefficients, okay. Then in addition to so this will be used to describe the series, this data. It's a very simple Transseries. But then there's other stuff we need. And that's kind of the stuff that replaces the assumption of the series being convergent. Okay. So instead of, we will not get a convergent series in this fact here, but what we will get is the following. We can find a bounded holomorphic function. So now I'm suddenly talking about complex analysis. And I'm going to call this f bar, right? F is my real term. F bar is going to be a holomorphic function defined on some domain omega, which I also have to specify. Where omega is what's called a standard quadratic domain. I will define this a little bit later. Just say it's a domain, right? So to be defined in a bit. What do I mean by that? And so this domain, what it does, I'm already going to draw the picture of this domain somewhere over here, maybe. Before I finish the full statement over on the right. And before I define the domain looks something like this. So here's my complex plane. That's the origin, okay? The domain looks something like this. I will explain how we define the domain right, in a second. It looks something like this. Now you're going to say, okay, what can this guy have to do with my original function f, which was defined on the small interval near 0? Right? It's not even in here. Well, we're going to have to translate from 0 to plus infinity. Okay, so f is defined on this domain, and if I take this germ here, translate it to infinity the right way, then this f bar will extend that real function f over here. So that's what I'm going to say next. Okay. So we do need two of these domains. Sorry, it's the last piece of data here. All right, another standard quadratic domain. Delta. So it looks kind of the same, but it's not necessarily the same one. Such that, so we have all this data now. Yeah, I can erase the fact here. Okay. Because I really just need that definition. So I understand the quadratic domain such that all of the following things hold. So, like I said, if I translate my germ to plus infinity, but not just by going from x to 1 over x, but by replacing x by e to the minus x in the logarithmic chart, that's sometimes called. This is the same as f bar restricted to the real line. Okay, so f bar extends the germ of this plus infinity. Holomorphic extension of that.
Your x is
No, x is close. Yes, right. So x greater than 1 over epsilon. No, sorry, no. X greater than the log of, what is it?
X big enough so that it makes sense.
Yes, exactly. There you go. Okay. Yeah, if you plug in large x, right, then this will be close to 0. So you can plug it into f. So this defines a germ at plus infinity, a real germ, and has a holomorphic extension. And this holomorphic extension in turn has an asymptotic expansion, which is that series that I'm going to construct from this. Okay. So for every n, natural number n, right? F bar of z, if you subtract this, right? So the series is going to look like this. The first term is just the constant C0 times x to the alpha 0. But after that, the next n terms are pi of x, oh, sorry, x, z. Right now I'm talking about complex. Okay. Pi of z, so polynomial is a coefficient. And since we are now in the log chart, right, we are talking e to the minus alpha I z here as the powers that appear in this series. So, right, this is a, well, definable in Rnx, for example, this function. Right? So I can subtract it from f bar. And this is supposed to approximate that function up to the order of the largest, the smallest monomial in this sum. So this is going to be little o of e to the minus alpha n times the real part of z. Right, so that's just the absolute value of e to the minus alpha n z. So
as c goes to infinity.
Right. This has to happen as z goes to infinity in omega. Okay. And finally, oh, there's one more condition from Ilyashenko. Right. This says something about this function f bar, the holomorphic extension. It's actually biholomorphic between omega and the other standard quadratic domain delta. Oh, sorry, not quite. So if you compose f bar with minus log on the left, then this is a biholomorphic map. So you have compositional inverse of the same kind of nature, or how it looks like, right? Okay, that's all the data. So suddenly, right, we go from not knowing anything about these maps to something like this. And again, this is a fairly hard theorem to prove. And I don't want to prove it. I just want to work with this. That's my goal here. Okay, let's see. What can I say about this to explain a little bit?
Don't you want to explain what quadratic domains are?
Yes. Oh, yes. I haven't done that yet. Right. I only drew the picture. All right. So here we go. What's a standard quadratic domain? Well, so standard quadratic domain is indexed by a positive constant c. Right? So there's one for each positive constant c. So that's the image under a certain map phi c of the right half plane. Let's just call it, no, that's not the right half plane, is usually the upper half plane. Okay, so no, that's not right either. What should I use for right half plane? C positive? Okay, so C positive is the right half plane. Okay. And phi C is the following simple map. So phi C is tangent to the identity, but then you have this term here, which moves things to the right, right? And the further up you go, of course, the further you go to the right. But what happens is that when you draw the domain, it looks something like this, and this curve here grows like x squared. Okay, because of the square root here. So that's what a standard quadratic domain is. Yes. Is what? Not in Ilyashenko's theorem, no. No, it's just positive. I know you would think it's one, but it doesn't have to be for what he does.
This last thing about that this map is biholomorphic seems so unlikely.
Yeah, well, yeah,
Don't you mean just?
it's not. If you don't assume this, right, you get more functions with satisfying the other properties. I think, yes, but Ilyashenko proves that this is the case for the correspondence maps.
Biholomorphic really meaning it's a bijection and the inverse is also holomorphic.
That's correct.
Ah.
Yes. Yeah.
That is a very strong.
Yeah. Yeah, but it doesn't matter for his definition of almost regular. He gets, but you can get everything out of it that he wants. So let's talk a little bit about that, right? So, for example, right. So now we have these Deluxe series, but let me I haven't named it yet, right? So the series, which is a Transseries, sorry, which I'm going to call P of F, which is C0 e to the minus alpha 0 z plus the sum I goes from 1 up to infinity pi of z e to the minus alpha I z, right? So a series in powers of e to the minus z whose coefficients are polynomials in z. So that's a Transseries, it's a very simple one. This is called a Deluxe series. Okay, because the first one to actually find this expression, this asymptotic expansion for this correspondence map was Deluxe. So yes.
First, you have in the previous part, you have set to the power alpha 0, not e.
Where?
To the minus.
Oh, yeah, that's sorry.
And then the sum runs up to n, not infinity. Is that also?
Yes, no, here I'm telling you that
Okay.
this series is an asymptotic expansion of f bar, which means for every n you have this relationship. Okay, on the domain. All right. Right. So again, to recap, right? If f were real analytic 0, we would have a convergent power series expansion at 0. So that would be my, when you translate it, right, it would be a convergent power series in e to the minus c. And that would satisfy certainly this relation here and everything else in this picture. But in general, for these maps, these correspondence maps, we do not have a power series, but we have this Transseries, the Deluxe series that appears. And in general, this Deluxe series is not convergent. All of this is known. Okay, so we would like to use this relationship here to conclude that when the series is 0, that then f has to be 0 or f bar, right? Which is what we use when we use real analytic. If you have a 0 convergent power series, it gives you the 0 function. Okay, and in fact, Deluxe, in his proof of his problem, he just assumed that whenever the series is 0, the corresponding f bar is 0, or actually the corresponding f is 0. He did not introduce all this other terminology about standard quadratic domain holomorphic extensions. So the key point that Ilyashenko introduced is that holomorphic extension part, right? And what he showed is that the holomorphic extension part together with the asymptotic property does imply that when the series is 0, then so is the function. This is called quasi-analyticity. And so that's what I would like to prove today. But before I do that, right, let's look a little bit more at these germs here, right? So this, right, this last condition here, no, this one, the biholomorphic condition, it kind of tells me that up to this composition with log on the left, right, F bar has a compositional inverse as a holomorphic map. On the other hand, if you look at the Deluxe series, just as a formal object, what do you get if you compose two Deluxe series, or more likely, right? So on the formal side, right, if I do the same kind of composition by inserting a log in between, right? So if, let F and G be two Deluxe series, then you can compose them in the following way. You can compose F with minus log and then G, and you get another, right? So this is all possible in a Transseries, but what you get is another Deluxe series. Okay. Yes.
When you say two Deluxe series, you mean two T of
Yes, of this nature.
or just
Right. This term of this nature here.
of different.
So include in particular the C0 here has to be a non-zero constant.
But could we take just formally satisfying the conditions? Like
Yeah, this is just formally, right? So Deluxe series of this form. When you compose them, you get another one of this form, as long as you insert the log, the minus log in between. In fact, the minus doesn't really
So
matter.
formally means that you do not assume all this business.
No,
about
no, no.
Standard quadratic
Just
domain.
given a series like this,
Formal series.
right? So this is a Deluxe series. So any series that looks like this, you can compose it like that, you get another one. And this is because of the assumption that C0 is a constant, not a polynomial. Okay. And in fact, also compositional inverses stay in here. Okay. Well, okay, that's a little tricky. What do I mean by compositional inverse? So the thing is, right, why do I have to insert this minus log here? That's because I'm in the logarithmic chart. What this means, right, if you put this together with that formal observation, it means that the composition of two almost regular germs is almost regular. Okay, so corollary, this, right? So this is, the other part is not hard. Once you have figured out this, the set A of all almost regular germs is a group on the composition. Okay. So that allows you to answer Deluxe problem for a vector field that has only hyperbolic singularities in this real analytic. Because the correspondence map, right, one way to recover the forward progression map from correspondence map is by taking the unions of all the graphs. Another one is by composing them. You can just look at the iterates of the correspondence maps, and you can still figure out where the fixed points of the progression map are.
little
Yes.
compose. I mean, this is a function f on an interval 0 epsilon to r. Does it follow from this definition that f takes small positive values? Does it go from 0 epsilon to 0 delta? For
Yes.
such
Yeah. That. Yeah. Right.
does that, let me see.
Oh, sorry. Yeah.
Does that follow?
No, sorry. That is a mistake.
Oh, okay.
Okay. So it maps. Right. And
You are assuming that in advance that.
yeah. Right. So
Okay.
that's right. Well, I think it does follow from all the assumptions that we have here. Right? This kind of assumption.
Patrick,
Yes.
Jean-Philippe, sorry to interrupt. In your exercise, I don't quite get why you put the log between big F and big G.
Because, well, you have to, otherwise you will get exponentials in here and double exponentials there.
Yeah, but if for example, if F and G are both equal to the identity, these are Deluxe transseries, right?
Yes. Well, no,
So
this is at infinity,
yeah,
and the original return correspondence maps are at 0.
but if you compose identity, then minus log, then identity again,
Yes.
do you get the Deluxe transseries?
Sorry, if you say that again.
Okay, if you compose, you consider F and G, big F and big G equal to the identity. These are Deluxe transseries, right? So if you put the log in the middle, there's something I don't get.
Sorry, what do you mean identity, right?
Z.
No,
F of Z.
these F bars are all bounded.
So Z is Z the Deluxe transseries for you?
No, right? So if you look at right here, this map here goes from infinity to 0.
Okay, but I just you are working with Deluxe transseries. Your exercise is about Deluxe transseries, right?
Yeah. Okay. Yes.
Okay, so Deluxe transseries, you put C0 equals 1.
Okay.
Okay, now I get it. Sorry.
Right, then you have
sorry.
e to the minus
Okay,
of
right.
0
Sorry
z.
for the interruption. You're right. You're right.
You do not have.
Absolutely.
So X is not a Deluxe
Transseries. Okay. Okay. Sorry.
because of that assumption.
Yeah. Right.
I have the feeling that C0 has to be positive in order for F to map positive elements. To positive elements.
Yes, you are correct. Yep, C0 has to be positive. All right, that is correct. Yep. Okay, any more questions? So these are all good points. It's a kind of weird, right? I am switching the point of view here now into this logarithmic map because not logarithmic chart, because I have to work in that later. So, but you have to switch everything. So what this means is composition for the correspondence maps in that chart corresponds to log composition. So maybe I should define what I mean by that, right? For these terms at infinity. So remark. Composition of almost regular germs right, so this is at 0 plus corresponds to log composition of regular germs F and G of F composed with this and G composed with this, right? I mean, that's kind of obvious. But that's why this thing here is interesting, okay? And that's why the biholomorphic property is interesting for these F bars composed with minus log on the left, because that corresponds to showing that the log compositional inverse is also of this nature.
Still can't believe that this.
You can't believe it.
That this map minus log composite F bar maps a quadratic domain exactly onto a quadratic domain.
So yes, well, okay, that's part of this, right, being a almost regular definition, but in the case where the map is a correspondence map, right, this is proved using the differential equation of the vector field and its complexification, in fact. Okay, so this is part of the proof of showing that it has all these properties. But I do not want to prove that because that would take me forever, right? I'm taking this as a fact. In fact, I'm not going to work with this specifically. I'm not so interested in that part, right?
What I can imagine is that it maps omega onto something that contains a quadratic domain. But you don't really mean that? You really mean?
No, it's actually a standard quadratic domain.
Oh, wow.
Yeah, that's what he said.
Okay.
So yes, it is. Okay, so right. So what do we want to do again? So for a vector field C, like we have now fixed, which has only hyperbolic singularities and is real analytic. Okay, we can conclude from this observation, Deluxe problem holds for C. So we don't need to know o-minimality of these correspondence maps, but still, right? So motivation is still that we would like to show, or I would like to show, is the expansion of, well, say the real field by all germs or some representatives thereof in A, all almost regular germs, o-minimal. Right, so that's the question that we were asking. So now I'm wondering, is it possible that they generate no minimal structure? Okay. So yeah, right, the question, trying to answer this question, we have various techniques now for proving o-minimality. Most of them include, things like quasi-analytic classes. And the question is this A such a class? Okay. And but even if it is, all the proofs that we know for such classes require the classes not just to be quasi-analytic, but also to be closed under addition, very simple things, closed under multiplication, and things like that. So known techniques would require A to be closed under addition in order to be able to prove this. Like known techniques mean, say, the paper by Rolla and Servi, right, which is a very general paper of proving o-minimality for quasi-analytic classes under addition, multiplication, and various other things. So But the class A, right, of all almost regular germs is clearly not closed under addition because of this property here. When you close under addition, you have two functions whose first term is the same. You want to close under addition, that means you have to add the difference of the two. Then you have an asymptotic expansion that's a Deluxe series with zero C0 coefficient. And that doesn't work. It's not in here.
You mean the difference? You
Yeah,
said
the difference.
addition, but you mean the difference, okay.
Well, of course,
right.
yeah, right. Closed under addition. So it's certainly closed under, no, closed under addition, but there's nothing like that. Okay, so you lose this term when you close under addition. And if you lose this term, and you have series that have an actual polynomial first coefficient, when you try to do log composition, you introduce new logs and logs, possibly, and so on. You get more complicated transseries. Okay. So that's a problem, right? In other words, the only structure the set has is this one. So it's a group under composition. It has no other structure that we can use to prove o-minimality. All right, so and then there is the other thing, right? So these techniques, like I said, they also require something called quasi-analyticity, which I briefly mentioned. And maybe now I should get a little more formal on that. So that is something that's true for this class. Okay, that's a key point in this in Ilyashenko's proof. So let me call this a theorem, right, due to Ilyashenko. And this is going to be very important for my attempt, right, to start to generate no-minimal structure with these maps. Okay, so the group A of almost regular germs is quasi-analytic. Which means the map T, right? So we have this map T, which sends each of the germs to its Deluxe series. From A into, well, for lack of anything smaller, just call it the Transseries, right? There's a map into the Transseries. This is injected. Right, and that's very important. That means if one of these maps happens to have or in this case, e to the minus z as its Transseries at infinity, right? Then the corresponding almost regular germ was the identity. Okay, so that is a crucial point in this study. So I do want to prove that. Hopefully I can finish that today. Okay. So, I mean, this is a fairly, I would say, a fairly classical theorem, but it's so crucial to what I'm going to do that I do want to prove it. That this is a course. So, so that involves a couple of things. Okay. The first thing it needs is what's called the Fragment-Lindelöf principle. Fragment-Lindelöf. So this is just about complex terms, and it has some, right? This is where the motivation comes from to study these holomorphic extensions. Okay, they are actually what gives us the injectivity of T via this complex analysis principle called Fragment-Lindelöf principle. Oh yeah, and this is due to, it's quite old. Okay. So it's just about holomorphic maps. Take a holomorphic map F on a sector of opening alpha. Be holomorphic. So what is this? Right, the sector S alpha, that's just a set where the argument in absolute value is less than alpha. No, sorry, no, that's wrong. Pi over 2 alpha, that's the one. Okay. And so I'm interested in alphas greater than 1, meaning sectors of opening less than pi over 2. Right? For alpha, if I equal to 1, I exactly get the right half plane. So anything, any smaller sector. So for such a holomorphic map, let's assume, make a couple of assumptions, right? So this Fragment-Lindelöf principle, that's right, that's a generalization of the maximum modulus principle, which only holds on bounded domains. Here we are talking about these sectors which are unbounded domains. And the maximum modulus principle for bounded domains says that the holomorphic function will always take its, that has a continuous extension to the boundary, will take its maximum values on the boundary. Right? So here, the only boundary we have are is the border of the sector, but the statement is pretty much the same, but you need some condition on the function in addition to get it. So here's what we assume. So first of all, we assume that the function is bounded on the boundary. Oh, holomorphic, yeah, I should say. And extends continuously to the boundary. Similar to the maximum modulus principle.
Including the origin.
Yes, including the origin. Yeah. Let's assume that it's bounded by some constant m for z in the boundary of S. So m is positive, and inside, right, we are just assuming that it doesn't grow too fast. Okay, so we're saying that as the modulus of z goes to infinity in the sector, it's bounded by some power of e to the minus z. So no power. It's absolute value e to the absolute value of z to the power beta. So as z goes to infinity in S alpha, where beta is less than alpha. Some alpha less than beta. So it's allowed to have exponential growth, but not too fast. It has to gotta be less than alpha. Order less than alpha. Okay. And then you can conclude that in fact f is bounded everywhere by m. Okay, so in other words, this assumption here immediately makes it collapse to being the much stronger assumption being bounded. right? With the maximum being taken in the boundary of S alpha.
Modulus of z.
Where? Who? What? Huh?
Modulus of f of z is below.
Does that matter? Isn't that the definition of big O? I mean, yeah, if you say big O, right, you're talking about moduli. Always.
So you claim more than the statement says now, right?
Hmm?
That you claim more than the.
Yes, right. So we don't, right? If a priori you don't know if F is actually bounded everywhere.
Yeah, but I mean,
You
you
just-
just that it's achieved on the boundary.
Yeah, on the boundary, right, of the sector. But there's a lot of space left that's not in the boundary. And all I'm assuming there is that it's not growing too fast.
And conclusion for the theorem, you said that you get equal to m on the boundary of the alpha. That would be-
No, no. I get the conclusion that, right, is that the maximum is taken on the boundary, yes. Because if M here, right, can be the maximum taken on the boundary and it still works. So then this is saying that the maximum is taken on the boundary in particular.
Yeah.
Okay,
If there is a maximum.
there is a maximum, yes, and it's taken on the boundary somewhere.
Let's see, is it obvious that there is a maximum?
Well, oh yeah, no, I guess no, because it's an unbounded boundary. So it could grow to M as you approach infinity. And then, true. Okay. So let me sketch the proof here. Right, and this, again, I want to prove this because I'm going to use this, as opposed to the other things I've been just mentioning. I don't really use them. They just put things in perspective. So the first thing is that, like, I can assume alpha is equal to 1. Okay, because if I replace f by f composed with e to the z to the, what is it, 1 over alpha? Yes, z to the 1 over alpha. Alpha is equal to 1. So S1 is just the half plane. The right half. Okay. So now what I'm going to do is I'm going to look at a family of functions. For epsilon greater than 0, define g epsilon on S1 by g. So I'm going to multiply f by e to the minus gamma z, where gamma is between beta and 1. And that's fixed.
You mean G gamma and Z?
Oh, that was the epsilon. There you go. Z to the gamma, and epsilon is a parameter.
Oh, I see.
Okay. That's the one I'm looking at. All right. So why do I do this now? So this is right. Epsilon is positive, so that means I have a negative exponent of x. So this is bounded. In particular, it's bounded on the imaginary axis. Okay. So then In fact, it's bounded on the imaginary axis by 1. So the absolute value of G epsilon of Z on the imaginary axis is at most M times, well, it's still M, right? Because the other part is bounded by 1. No? Am I correct? Yep. For Z in the boundary of C plus. So the imaginary axis. Okay. Aha. And what's the growth? Right. Well, so for any Z in the right half plane, right, the absolute value of G epsilon of Z is at most e to the well, okay, e to the real part of this, which is minus epsilon. What is it? The real part of Z to the gamma times f of Z, right? All right. So here, what I get is that's going to be, oh, there's a constant here because we have big O, which involves a constant. Okay. All right, so that's really C times, now I'm going to write exponential, because otherwise this gets too, if it's in the exponent, it's not clear what it looks like. So we can write C to the beta, that comes from the assumption on F, right? Minus this stuff. Epsilon times, and the real part of C to the gamma, that's really modulus of Z to the gamma times the cosine of gamma times the argument of Z. Okay, so what do we have here? Gamma is less than 1, right? Yes, it's less than 1, which means the cosine here is positive. Okay, gamma is also greater than beta, which really means that this part here dominates, the negative part in the exponent dominates. So this actually goes to 0. Okay. So this goes to 0 as Z goes to infinity. Aha. So see, now what I'm going to do is I'm going to apply the maximum modulus principle on bounded subsectors of the right half plane with the same opening. So for C large enough, right? The value of the function G epsilon along the circle of radius of that is less than M. Okay. Because it goes to 0 uniformly in the absolute value, right? So the max, well, by the maximum modulus principle, that means G epsilon. No, what am I trying to conclude here? Yeah.
It will be less than equal to M everywhere.
Exactly. G epsilon of Z will always be less than equal to M for all Z in C plus, right? Because it's true in all sufficiently large bounded subsectors, so it's true everywhere. Okay, but that now means what? It means that f of Z is less than or equal to m g of c times e to the epsilon times z to the gamma.
You let epsilon go to 0.
Exactly, right? For all z in C plus, and for all epsilon, because epsilon was an arbitrary parameter in that. So if I let epsilon go to 0, this approaches 1, right? Letting epsilon go to 0 gives f of z less than or equal to n for all z. Okay, makes sense? It's so this is an old theorem, like I said, 1908, but it's very useful. So I want to keep the standard quadratic domain up, so I'm going to go back to this. So this is not quite enough, though, for us. So what we're going to do with this is the following corollary, which is now in this form due to Ilyashenko. You can find this right in the book by Ilyashenko and Yakovenko. By the way, this whole treatment is from there. There's nothing I invented here. So let's take again a holomorphic function on C plus. Well, again, okay, this now it's just C plus. Okay. So the idea is, right, on this, in this Feynman-Lindelöf principle, we had to have the assumption of exponential growth of order a bit less than alpha. Okay. But in fact, there's another way that we can get order exactly alpha, right? If we make another assumption instead, and that's what we're going to do here with the half plane. So let it be holomorphic on the half plane again. Holomorphic with continuous extension to C plus bar, okay? And now we're going to assume that 1, again, f is bounded by a certain number m on the boundary of C plus, so on the real imaginary axis. So this m is given. And 2, again, I have a growth condition. F of z is big O of E. And now if the order is 1, right? Before we had to have this order beta less than 1, right? In the Feynman-Lindelöf principle, in the classical one. But now we are allowing order 1. As z goes to infinity. Okay, but that means we have to do something else. Okay. We are also going to assume that on the real line, so on the positive real line, f is bounded. Not by m, just bounded. So the restriction to the real line is bounded. Then again, we have the conclusion that the maximum is taken on the boundary of the half plane. And so it's f is less than or equal to f. F is less than or equal to everywhere. All right, and So I'm a little embarrassed to say that yesterday I spent probably 2 hours trying to understand this proof, when in fact, like with all these things, it really isn't that hard when you put it right. Okay, so right, so we are talking here about the half plane. Okay, have a function on it, but now we have our desired bound, right, on the imaginary axis. So that's where the desired bound M holds. And there is some bound that we don't know on this half line. Okay, so let's call it N. So here, maybe I should write it like this: f of z on the positive real axis less than or equal to N. From that, I want to conclude that everything is bounded by this one. And then I have the assumption of at most order 1 exponential growth on the half plane, which is now too weak to directly apply the Fragment-Lindelöf principle. But the trick is, right, this half plane is made up of 2 sectors of opening pi over 2. This one here and this one here. Okay, they're not bisected by the real line, but you can move them so that they're bisected by the real line of opening pi over 4. Both of these. Okay. So you apply the Fragment-Lindelöf principle that we just proved to each of those sectors, because now we have opening pi over 4, and we have exponential bounds of order 1, which is okay in this case, right? So, right, pi over 4, that corresponds to alpha equal to 2. Okay, so apply the Fragment-Lindelöf principle with alpha equal to 2 and beta equal to 1 to each quadrant.
The idea is that you can rotate this quadrant so
Yeah.
that
Rotation is just multiplication by a
Okay.
complex constant.
so that the symmetric will
Imaginary.
affect the real.
Yeah, right, exactly. So to each quadrant, to obtain, well, what do we obtain? We obtain that in this quadrant here, f is bounded by the maximum of m and n, and in the other quadrant. So we get that f is actually bounded from this. We just don't know yet what the bound is. F is bounded. But now, right, being bounded is much stronger than being of exponential growth less than 1. So now I can apply Fragment-Lindelöf again to this f on the whole half plane with alpha equal to 1. Right. So apply pH again to f with alpha equal to 1 and beta equal to 0. Right? Being bounded means we take beta equal to 0. And so now you're done, right? Okay. All right. So, sorry? Alpha equals 1. Yes, sorry. Beta equals 0. Okay, so now finally we get what we really want for our quasi-analyticity. Again, this is Ilyashenko's theorem, and it can be found in Ilyashenko-Yakovenko's book. And I'll call this the uniqueness principle. Okay. So now we're talking about the functions, the extensions f bar there that we get in the process of almost regular maps. So take a map F defined on some standard quadratic domain, right? Holomorphic. With continuous extensions to the boundary. Okay. And let's assume two things. So one is that, again, it's bounded by some number n on the boundary. Okay, so remember, right, these functions over there, they are supposed to be bounded, those holomorphic extensions. And two, what we're trying to say is that if its asymptotic Deluxe here is 0, the function should be 0. So what does it mean to be having an asymptotic Deluxe series equal to 0? It means that the function is exponentially flat is exponentially flat, right? At infinity. So f of z is where is it?
Little of e to the.
Oh no, sorry. No, that's not what I want to say. First, I want to say that it's still. I'm only assuming it's exponentially is of order at most 1 in the domain. Okay, so f of z is big O of e to the mu z times alpha value z for as z goes to infinity in omega. Okay, so it's exponential growth, but
What is this exponent there? Mu?
mu, right? Mu is some positive number.
Oh, mu is a positive number. Okay.
Okay, but along the real line, it's going to be flat, like these terms when you have 0 expansion. So I mean, these terms have 0 expansion in the whole domain, but whatever. All I need here is that along the positive real line, f of x, so I write x here to indicate I'm just looking at positive real numbers, right? F of x is actually little o of e to the minus rho x as x goes to infinity in R plus for all rho. Right, that's what it means to have 0 asymptotic Deluxe expansion. Then f is actually 0. So now I'm wondering, yeah, I guess I should stop here. I'll finish this next time. It's probably a good reminder. Right, standard quadratic domain. This is a standard quadratic domain. Yes. Yeah, I'll finish this next time. It's not very long, but
Do you use some sort of transformation
Oh,
from omega onto a sector or the?
well, under the half plane, right? Remember,
Yeah.
omega is the image under that map of a half plane.
Oh yeah. Right.
So it has an inverse.
Ah.
That phi c is invertible,
Okay.
and it's tangent to the identity. So
Oh.
the conditions that we have listed here still hold for the pullback of f to the half plane. So I can assume omega is the half plane. And then when it's the half plane, we can just apply, right?
Corollary 7.
This means it's more than just bounded, right? So I can apply corollary 7 to f multiplied by e to the rho x for every row. Okay, to conclude that f times e to the row x is going to be bounded by m, always the same m. Aha, but then let rho go to infinity. Okay. That means f itself is bounded by m times e to the minus rho x everywhere. Let rho go to infinity. It means f has to be 0 everywhere.
You need the boundary not to be, the boundary has to be like this.
Hmm?
Otherwise, whole. Because the right of the model of both and second. That would be accurate.
Yeah, but I'm sorry.
I mean, you have to be on the, but that's the thing. Only that is fact f. I mean, when we f times exponential of 4 times.
Yeah, so this assumption really only has to hold along the real line in the quadratic domain. But in practice, it actually holds on the whole domain, yes. In those. But for the conclusion here, you only need to know that along the real line. And you need to know this elsewhere. Okay. Anyway, so I guess we could say that finishing this is an exercise. It's again, so you look at this family of functions, f multiplied by e to the row x. Okay, apply this corollary to each of them. And then from that, you can conclude f had to be 0 everywhere. Okay. All right. So I'm going to use that a few times in the remaining lectures.